So here we have our two example tasks from the clinical routine. So those are the two tasks we want to build an AI model for. So we have the lymphoma segmentation. So here the model should be trained to locate all the lymphomas in the body and to segment them. And down here we have the prediction task. So here the AI model should learn to predict which lymphoma comes back within the next 5 years. So, and we already discussed what we need to train those AI models. And we said first we need some NVIDIA GPUs. Well, then we need a programming environment for the programming language Python. So, and then inside Python, we need the PyTorch library. So it's a library with all the functions you need to build an AI model and also everything to train an AI model on NVIDIA GPUs. So now we already said, when we have that, we can start coding and then start the training. Yeah. So now we want to go a little bit more into detail how we do this programming, this coding with PyTorch. So the first thing we need there in PyTorch is a data loader, because we need to get the data into Python. So in PyTorch offers some data loader functions you can just use and then set your path to the data set. So, and then the next thing we need is we need a deep learning model. So those are those models here. So the AI model, the model with many variables, where the variables get changed and in the end set perfectly during the training. Yeah. So, and PyTorch offers many deep learning models we can choose of, and if you don't find anything nice here, you can also look at Hugging Face. So it's a US company that offers, which has an open source library for deep learning models. And then you can also look at Monai. That's also an open source Python library from NVIDIA, and they have many special medical models. Yeah. So, and yeah, now we want to go a little bit more into detail into those deep learning models, how they look like. Yeah. So in general, for imaging tasks, there are two kind of models. Those are the convolutional neural networks and the vision transformers. Yeah. Well, and the convolutional neural networks, they were developed specifically for image classification tasks. And they are less computational intensive, so you need a little bit less of those NVIDIA GPUs. And also, if you don't have that much labeled data, the chances are higher that you still get some good results with convolutional neural networks. Yeah. Well, then the vision transformers, they were originally developed for text by Google, and then in 2020 also adapted for images. And they are more compute intensive, so you need more of those NVIDIA GPUs for them. But and also they need more data to be trained. Yeah, but if you have a large data set, then normally mostly they achieve the better results. Yeah, so those are two models. Well, and how do they work? So let's say we have an input image here, and this image consists of many pixels. So let's say this is a pixel, this is a pixel, this is a pixel. Of course, there are in reality much more pixels, but to keep it simple, let's say those are the different pixels. So in each pixel has a grayscale value, so that shows how grayish or blackish or whitish this part here is. Yeah. So now those two models, the convolutional neural network, the vision transformer, they have a lot of matrices with variables. So this is a variable, this is a variable, this is a variable, yeah. So and they have a lot of them, yeah. And now there happen a lot of calculations between those pixel values of the image and those variables here. And in the beginning, you just take some random numbers for those variables, and those are the variables that are then changed during the training. So in the calculations are some, yeah, additions, subtractions, but also multiplications, also some nonlinear functions, so a lot of different things that are going on there. Well, and if you're interested which specific calculations happen there in a convolutional neural network and in a vision transformers, and what also is the difference between those calculations, then you can look into this YouTube video, and I hope this should be also shown now at the corner where you can directly click on it. So there I go into detail what calculations happen in those two models. But in the end, it's not so important to know into detail which specific calculations happen there. Because in the end, you will just take a model from PyTorch or Hugging Face or Mona, yeah? And the thing is, there are millions of possibilities about what calculations you can do in there, yeah? So, and big companies with many NVIDIA GPUs, they just tested many different combinations and then found some good models for specific tasks. So, and I listed here a few models which are in the moment state of the art for segmentation and state of the art for classification or prediction. Well, and some of them are based on convolutional neural networks, some are based on vision transformers, and most of them were developed by Google, Meta, or NVIDIA. And yeah, just to give a rough number, so they have between 10 and 800 million variables. Yeah, so and this is also why most people refer to them as black boxes, because there's so many calculations going on with so many variables. Nobody can really say what's going on there. Yeah, so that's not something that humans can really understand. Well, and of course, there's always a lot of research going on, and then constantly new models pop up. So, and in the end, you normally just test different models and see what works good for your task. And it's not so easy to say before which will be the best model here. Good, now we have a deep learning model. So the next step is we need a loss function. A loss function are those error functions here. So this is where we calculate the error between what the model outputs and what it actually should be. Yeah, so the model output is the model prediction. Yeah, and then what it actually should be is in this case here the lymphoma segmentation by well-trained radiologists. So where the lymphomas actually lay, or down here the ground truth, what it should actually be is whether the lymphoma came back or not, because we know it because those scans are more than 5 years old, so we know which lymphoma came back or not. So this is the next thing what we need, the error functions, and here are different PyTorch as different loss functions you can choose off, and like the mean square error, for example, here, but also different ones, and you can just try out which works best. So then the next step you need is the optimizer. The optimizer is the thing that changes the variables in the models. Yeah. So and the optimizer is basically a mathematical minimization. So and let's say we would only have 3 variables here in the AI model. Well, and then you could plot this like this. So it looks like some hills, like if you are in the Alps or something, right? And this is then the error function. So let's say we have now calculated. So in the beginning, here are some random variables. Yeah, we just take some random numbers. Yeah, and then we are just somewhere here in the mountains. We start somewhere random. That's, for example, here at this point. Yeah. So now, step by step, which with each time a new image comes through, we want to come closer to the minima, where this arrow here gets minimized. So this is where we want to go. Yeah. And this happens then step by changing the variables to get into the minimum so that the error is minimized. Yeah, and also PyTorch offers then different optimizer functions that you can try out, which works best here. So, and there are also some values you can adapt, like the learning rate, how fast you go into this minima. Well, okay, then we have this all together, what we need, and now we can build a training loop. And I already told that in the beginning we split up the data between training and test. So we use the training data to train the model, and then on an independent data set, which we did not use for training, we test the model if it works in the end. So now we take the training data set and split this up again into training and validation. Let's get a little more space here. So now we start with the data loader, okay? So, and we load some images from the training data set, so from this part here into Python. So now we take the images, put them through the model, and the model outputs something. So the model gives some prediction, like here, this output here. So now the next step is we take the loss function. The loss function is the error function, so this here, and we calculate the error between what the model outputs and what it should actually be. So what, for example, a radiologist said it should be. So, and then comes the optimizer. Yeah, so then we update the variables in the AI model. So now we can take the data loader again, yeah, and now, but this time we now load a few images from the validation data set. So before we loaded the images from the training data set, now we load them from the validation data set. So, and now again, we take those images, put them through the model, and the model outputs something. So, and now we again calculate the loss function, the error, so how big is the difference between what the model says and what it actually should be. But this time we do not update the variables. So with the validation data, the model is not trained, yeah? So we just use the validation data to track our training, to see how good the training is developed, yeah? So that's just for validating, but we do not update the variables. Now, and then we start up here again. Then we take again the data loader and load some training images. And we go through this several times until we are several times through the data set and until the model is trained. So, and while we do that, of course, we track the training. So, and here on the x-axis, we have the training steps. So how often are we through those the training images? And here we have the loss function. So here we have the error function. So here we see how big is the error between what the model says and what it should actually be. And in the beginning, the error will be pretty high. So the first training steps, the error will be high because the model doesn't know what it should do, right? So the error between what the model outputs and what it should actually be is high. Well, and then ideally, in the beginning, the training loss and the validation loss is going down, yeah, because now we always update the variables with the training data, so it should get better step by step. Well, and then here happens something which we call overfitting. So here the training error is still declining, it's still going down, but the validation error is going up. So, and what happens here is that the model is now overfitted on the training data. So the model knows now perfectly how the training data looks like, how it works, because the training data is what we use for always updating the variables. So the variables are now perfect for this training data, but only for this training data. They are overfitted on this data. They're too much trained for this data. So it doesn't work anymore if we take different data which is not used for updating the variables. So, and this is the validation data. So this is why the error for the validation data is going up. So, and this is why, but of course, in the end, we want that the model also works for data that it didn't use for training, yeah, because that's what we want. We want to use that in the end in the clinical routine with new images, of course, of the same type, but not the specific images we used for training. So this is why here we should stop the training. So it's not the longer the better. We need to find a sweet spot, yeah, for training. So this is where we need to stop our training. Okay, so now we have a trained AI model, yeah. So, and of course now you compare different models, you compare different losses and optimizers. Well, and then if in the end, if you have a good model, then you test the model on an independent test data set. And that's very important. That should not be this validation data set. That's to validation data set is to use to find the perfect position where to stop, or maybe also to compare different models or loss functions optimizers. But now you have to test it on an independent test data set, which you lay to the side at the beginning and never touched it, or even better, you send it to a different hospital and they test it there. Yeah, so this was like the in-depth informations about how this AI model training is going to. Yeah, then thank you for listening.